Hi guys, Mark here from XPS, back with another video, and today we're going to be looking at some sample damage in XPS and how we can compensate for this and overcome some of the difficulties involved when you do have sample damage. So to get us started, we're going to have a look at a couple of things here. We're going to start off by looking a little bit at some soft materials, so some of the work we've done on materials that aren't particularly stable in UHV, followed by a look at some Ceria-based materials. Ceria is, of course, a very important material in a lot of things like catalysis, energy materials, etc. And finally, just a couple of solutions, how we can overcome some of the challenges involved with X-ray damage. So if you're not familiar, when you have materials in a UHV system, X-ray and electromagnetic radiation can actually do some kind of damage to your systems. Exactly the processes of those depend a little bit on what the material is, but of course if we do have any kind of damage like this is incredibly important to know what damage is being caused and how we can minimize the impact of this, because of course if we do have damage changing some of the chemistry in our surfaces, then this could lead us to some erroneous conclusions about the materials that we're working with. So we do need to look to overcome these, minimize those. So as I said, the first thing we're going to look at is a soft material. So we're going to be looking at titanium butoxide. That's this molecule here. It's very common in a lot of inorganic synthesis, particularly for things like photocatalysts, and it's actually unstable in UHV, so we have to cool this molecule down to even measure it. The vapor pressure is such that if we try and load this into a UHV without any cooling, it will just evaporate. So we need to get down to about minus 50 degrees C to even get a measurement at all. But we have this additional challenge where if you do expose it to X-rays under UHV, you do start to reduce this titanium center. So to visualize that a little bit, the first image we're looking at here, so at minus 120 degrees, so very cold. We've just taken an image from the internal microscope on our Kratos Supra system before and after an extended exposure to X-rays. And if you look closely, you can see a dark discoloration on the exposed sample. Now this is obviously where our beam is hitting the sample, and it's the first visualization that we can see that we're doing something to our sample that is obviously not great. We're changing it, and of course first rule of any measurement is you don't really want to be changing what you're looking at. So to visualize that in terms of the actual chemistry, if we look at the figure on the left, we can see around 456 a bit of a shoulder start to appear as we increase the exposure time of X-rays, and this is due to the formation of some titanium 3+ states. So when we quantify these, as in using the graph on the right, we can see that we're starting to, after a period of initial reduction at quite a rapid rate, we do plateau off, but we're ending up with about 15% titanium 3+. When these materials start to stabilize under the X-ray. So clearly this isn't representative of our sample, and is going to cause us some difficulties when it comes to trying to understand the XPS spectra and the signals produced from this. So the second example of X-rays damaging or reducing a sample is Ceria. Now Ceria is very commonly looked at by XPS. It's a very useful oxide in catalysis, especially where XPS is widely used, and understanding this amount of Ceria 3+ relative to 4+ is critical to understanding a lot of the processes involved and understanding what makes a good catalyst perform how you'd like. So the quickest and easiest way to visualize what kind of reduction we're seeing here is to look at these two figures here. Now on the bottom we've just got a very quick scan of just a commercial Ceria we brought in, small amount of Cerium 3+, but mainly Cerium 4+. If we actually leave the X-rays on for 60 minutes, you can see we form a huge amount of Cerium 3+. Now of course if you're looking at a material where you might need to scan for a number of minutes, if you have a small Cerium trace, etc., then it's easy to see that you're not going to be getting reliable data because you can induce this reduction. This is a well-known effect. There's been many people that have observed this in the past, but it just means it's really important to get your experimental parameters correct to minimize this effect and to, confirm that you've got what you think you've got in the material. It's also quite common nowadays, or relatively common nowadays, to include Raman, so coincident Raman in XPS. And what we've recently observed is that in UHV, even the Raman lasers themselves can reduce the cerium 4 to cerium 3 as well. So these are some Raman spectra from just a commercial seria on our Thermo Nexa. And we can see the initial scan on the bottom in blue, where we've taken a Raman spectra of this seria, and we've got the characteristic peaks. After 15 minutes, this cerium 4 plus signal from the Raman laser is completely destroyed, because we've just reduced all of that cerium 4 plus down to 3 plus. And if we look at the XPS of a pre and a post exposed sample at different Raman laser powers, we can see this effect of the power of the Raman laser on the degree of reduction of the cerium sample. So if we have a relatively higher powered laser, we get almost immediate reduction, whereas if we tune the laser power down a bit, we can slightly start to prevent this reduction from happening. So what kind of solutions have we got to overcoming X-ray damage? Well, firstly, we've already spoken a little bit about temperature and how some samples we need to cool to get any data at all. But the effect of temperature on, for example here, our titanium butoxide system, is that the colder we get, the more we can actually prevent this reduction from happening. So we've got two spectra here, one taking at minus 60 degrees C, one at minus 120 degrees C. And you can see a drastic difference in terms of the amount of titanium 3 plus that's been produced by this X-ray damage. And if we look at the quantification on the right, you can see that after a short period of measurement, we've got nearly 50% titanium 3 plus at minus 60 degrees, whereas when we get down to minus 120 degrees, we've reduced this down to less than 10%. Sample optimization. So in a lot of modern spectrometers, it's quite common to have an auto Z function, so you can put your sample in, turn the beam on, and tell the software I want to essentially find the height of the sample, line that with the focal point of the X-rays. Now, of course, while you're doing this, the X-rays are on, and this is going to be doing some sample damage to sensitive systems. So the orange column here is the amount of titanium 3 plus when we use the auto height function, and the blue is where we've done a manual height optimization. So this is just using the internal cameras and microscopes of the XPS to find the optimal height of the sample and not use the X-ray signal itself, because then we prevent this sample damage from having our X-rays on during the auto height. And this does of course mean that you need to have a well optimized camera to focal point position, but you should be looking to have that anyway. So this is one way that you can again just minimize the amount of reduction in your sample. It's also perfectly acceptable to use the auto height function on one location and then move to another part of the sample which is at the same height but hasn't been exposed to X-rays already. So this is just another example of cerium 3 plus to show that we see exactly the same thing. So this was actually on a different spectrometer. The previous was run on our Quasar Supra, this is run on our Thermo Nexa. They've both got auto height functions, just showing that we do see exactly the same thing regardless of the system. Multiple scan areas. So if you do have a system where, for example, you may have a smaller amount of cerium than in a bulk seria, you might want to do more than one sample analysis spot. Now this does kind of run on the assumption that your sample is homogeneous, but if you do have a sample that is particularly heterogeneous, then you'll want to be looking at taking multiple areas anyway to get a good idea of how the surface kind of changes and the overall composition. But essentially the thought behind this is, if you have a sample that is reducing, if you take one scan from 9 individual areas versus 9 scans from one area, the amount of reduction in the 9x1 sweep is going to be less and more representative of your actual sample. There's a lot of really nice functions in modern spectrometers. Again, Thermo and Kratos both have functions where you can put in kind of area scans and very quickly get multiple analysis regions of different areas, which can then be combined into a cumulative plot in Casper XPS, so you can get the good signal to noise of multiple scans but avoid the downside of having a reduced material. X-ray power is another important factor, so again it's going to be a bit of a balancing act between getting the appropriate signal to noise that you need to get the data quality that you need to understand your material, and also minimizing the reduction. So here we've just picked a couple of different X-ray powers, and you can see once we get down to about 5 milliamps emission, we are drastically reducing the amount of reduction that we see in our sample surface. So again, if you can play around with that a little bit, find the optimal positions and the optimal parameters, this will go a long way into getting a reproducible and reliable representation of your surface. So finally, the other thing to think about is your neutralization system. So charge compensation systems for insulating samples typically use a low energy electron flood gun. Some systems, for example the Thermo XPS systems, use a dual neutralization system which has a combination of low energy electrons and low energy argon ions. Now, one of the potential drawbacks of this is if you have a sample that is susceptible to damage from those argon ions, you might need to think about your flood gun settings. So an example here from our some work from our technical director David Morgan with Thermo, looking at how chromium systems behave when exposed to a dual neutralization system versus just an electron flood gun. And what you can see on the left, where we have the dual neutralization on, is that chromium 6 is readily reduced into chromium 3, whereas if you have just the low energy electrons, we do prevent this reduction from happening. So one of the ways we would look to monitor this is to run a continuous XPS spectra with the flood gun on, and then take snapshots of our sample at set time points with the flood gun on, and then expose the sample to X-rays with the flood gun off. So we've got an example from our Kratos Super on the left and the Thermo Nexa on the right, for our cerium systems that we were looking at before, just commercial ceria. And what we can see in this case is when we plot our snapshots where we've been running with the neutralization system off and then just turned it on for a single scan, these lie on exactly the same axis as when we just run the entire scan with the flood gun on. So we can be confident in this scenario that our neutralization system isn't doing anything to our ceria. This is just X-ray reduction. But it's just another thing to think about. If you are noticing some kind of sample damage, it might also be the neutralization system, not just the X-rays. So thanks a lot for listening. I've got a couple of quick thanks. So as I mentioned, David Morgan, our technical director, Chris Parler, Rob Palgrave is the director of Harwell XPS, Roxy, one of his PhD students, and Cheryl Lampos, a former postdoc at Harwell XPS. So thanks to all of them for contributing various bits of work to some of the studies in here. Thank you guys for listening. There'll be some more information about this kind of stuff on our Guru website, so if you haven't been before, check out harwellxps.guru. Lots of pages, information on different aspects of XPS. And again, as always, if you have any questions, do get in touch with us either in the comments below or at inquiries at harwellxps.uk. I will put the links to the papers where we discussed some of the reduction and ways of overcoming this in the description below. But until next time, have a good one. I'll see you soon.